Okay, Assalamualaikum warahmatullahi wabarakatuh, and very good morning to everyone. Thank you for coming to my class. I'm so sorry about the a bit late that we start. I have a slight emergency meeting. Suddenly, I want to start the class. People go for meeting. This is the problem with working online. You know, people from all over the world can call you meeting at any time, and they know that you will come because you're just in front of your computer. That's the problem. Okay, I think I have received several for the previous class. I have sent you the recorded video for our session. I think I've talked about least square estimation. I've talked about generalized least square estimation, and then I have talked about how least square estimation to be used with a bulk of data. Let's say we have 1,000 data. How can we rearrange the data so that we can develop the program in MATLAB? And I already show you the MATLAB programming on least square estimation and also recursive least square. I've talked about recursive least square as well, isn't it? Okay. The most of the feedback that I got, okay, I think that's good that you have a feedback, means you've gone through my video. I'm worried that you did not go through my videos. Okay, so it's good that you got a feedback saying that recursively squared, you are having a little bit of problem understanding the derivation, isn't it? I have several people, I think half of the class is having the same problem. Okay, I don't blame you, because looking at one video, it's very difficult to understand the derivation. When I did my PhD back in 2000, year 2000, it was 20 years ago, and I have to develop a recursively squared program. It took me 3 months to understand the derivation. I was only 24 years old at that time. So yeah, it took me 3 months to understand least square, recursive least square. So I don't expect you to understand just by looking at my slide and just by looking at my simple video description. It's difficult actually. The algorithm, the derivation is actually very difficult. Okay, so don't worry so much about it for not understanding recursive least square. Okay, so what I want you to know is that how the recursive least square is actually can be utilized for adaptive control. All right, so I'm never going to ask you how to derive recursively squared. Okay, and I also never going to ask you in tests, for example, to use least squared with given data and try to get estimated parameter. Is impossible, because it's very complicated. Okay, the equation is a bit complicated. Of course, if you study it for 2 months, maybe it takes me 3 months, maybe you with the technology 1 month. Okay, if you study it for 1 whole month, maybe you'll be able to understand overall. But it's not for examination. Okay, so don't worry so much about it. Okay, it's not examination material. It is more for you to utilize for your research. Let's say you're doing your master project, you're doing your PhD later on, then I will ask you to indulge in the algorithm, and then we will explain you more on how the derivation of recursively squared. But not for this class. I'm not going to do that. It will take me ages to explain to you. That's why I just show you how the mathematics is working and how it's being derived, but I don't ask you to actually fully comprehend the derivation. It's actually take times. Okay, so don't feel too bad about it. I'm not gonna ask you to have it in your test or in any of the exam, or not even using 10 data and then get parameter using recursively squared. It's not that. Okay, it's impossible to do that. Is all right? Okay. So it's just for you to know about it. Okay. However, for simple least squared, for generalized least squared, yes, it will be asked in your test, and also I will ask you to develop programming. I already sent you the algorithm, isn't it, for least squared and recursive least squared. So I hope you can go through the how that mathematics being written in MATLAB programming. That's all. I need you to understand how that mathematics been transformed to the MATLAB coding. Okay, so that later on I mentioned I'm going to give you assignment last week, but I think I want you to relax a little bit, so no need. Just try to understand the program that I gave you. Okay. I'm going to give you this week that assignment. It is actually to write the generalized least squared as extended of the program that I give you, the least squared program that I have given you. Okay, so I want you to extend it and use generalized least squared to update to filter your data using MATLAB, and then to actually come out with the new estimated parameter. Okay, after you have done your filtration of data, and this can be done not only once, twice. For exam, maybe with handwritten hand calculation. Maybe generalized least squared can be asked maybe one time, because if I ask you to do 2 iteration, it will take you more than 3 hours maybe to calculate. Okay, so, because you're not using software, isn't it? But if you use software, of course you can have 100 iteration, 1000 iteration. Doesn't matter, isn't it? Because it takes a split second for computer to do it for us. Okay, so what I want you to do is to write a simple program, okay, on generalized least squared. Either you can use the existing program that I have for least squared and extend it, or you can write your own least squared and then have generalized least squared as part of the loop that you are producing in your MATLAB. Okay, so that will be your assignment. Is that all right? Okay, so for recursive least squared, maybe I'm just going to show you again the slide on recursive least squared. So this is the slide that I've shown you before, recursive least squared. Can you see?
Yeah.
Okay.
Right. This lecture is recorded.
It is recorded. Thank you. Thank you for reminding. Okay. Actually, when we want to use recursive least squared, it is the most desirable conventional method compared to least squared. Okay, why is it so? All right. For example, when you want to do a controller for air conditioning system, for example, okay, so let's say you need it to be adaptive because there's a lot of variable that is actually air conditioning system. There's not much variable, okay, and it doesn't change. Okay, you don't need adaptive control. This is just an example. All right. So when you want to know what is the current temperature, you have to collect the temperature and you have to have a set of data, isn't it? And for temperature, the changes is not as dramatic like vibration. For vibration, if I run my vibration of flexible beam just now, if I run the test rig, I push the test rig and it will move, within 4 minutes, I will have thousands of data. Okay, I can collect the samples of data every 3 millisecond, for example, and I will have thousands of data within 3 minutes, right? Okay, so but not as the case of air conditioning, because air conditioning, it will take you time for it to change from one temperature to another temperature. Maybe even with a lot of disturbances, a lot of parameter changes, maybe it will change from one temperature to another temperature within 10 minutes, okay? Maybe within 5 minutes. So one day, maybe you can collect at most how many data? Not much, isn't it? Maybe the whole day is required for you to collect 3,000 data, 4,000 data, okay? So for a conditioning system, if you use least squared, all right, you remember least squared, the estimation is going to be better if you have more data, isn't it? Okay, so when you want to collect 10 data, for example, you have to wait for more than 1 hour, isn't it? So when you want to update your controller, it's not possible to do it real time because your data is not enough. So when you start collecting the data, okay, you collect the data and then you need to have more data before you can use least squared. If you only use 4 data, 5 data, it's not enough. Okay, so for lower order, maybe it's okay. For higher order system, it's not enough. Okay, so for you to do this, you need to have another algorithm which is called recursive least squared, because recursive least squared, when I show you the demo last time for MATLAB, you've seen that least squared estimated better than recursive least squared. This is simply because least squared utilize all the data that I gave them at one time. Okay, so when you have that data given to you, it will use the whole batch. One, let's say 4,000 data, they will use all 4,000 data at one time and do one prediction. Okay, so of course the prediction error will be very small, and the prediction is really good. Okay, but in reality, in the implementation wise, it's not that way. It doesn't work that way, isn't it? You cannot collect the data for air conditioning system for one whole day and then you want to use it to control the system. By that time, you already switch off your air conditioning system, isn't it? Because you want it to control. When you switch it on and it doesn't perform the way you want it, maybe you want it to take time, maybe within 1 or 2 minutes before you get comfortable with the air conditioning system, isn't it? So you don't want to wait for one day before the air conditioning system give you the temperature that you like. So this is not really very good to use least square to estimate the parameter of your system for this kind of system. All right. So for this kind of system, if you use recursive least squared, even though the estimation is not really very accurate compared to least squared, but you can use a minimum number of data. All right, so it means to say you collect 4 data, you quickly update the parameter of the system with 4 input and 4 output. Then at the same time, you keep collecting 4 new data and then you update the model every now and then. So this is how you do it, okay? So it is better compared to if you need to use more data. All right, let me just show. Where can I show? Can I use this one? Okay. So for example, if I have a system, okay, this is a real system. Okay, so I want to control this system, okay? So, but I do not know the transfer function. So how can I design the controller, isn't it? I don't know the transfer function of the system, okay? So what I do is I disturb the system. I give a response, I give a input to the system. I disturb it, okay? And then I let the system respond it, okay, according to my input. So then I use my sensor, okay, to collect the input and output of this system. All right, so I will collect the data, input and output of this system, okay? All right, and then I will use the method that I have used before, either is least squared or recursive least squared. But if I want to use least squared, I need to have maybe 4,000 data, right? Input and output. So that will take me time, right? When I collect the input, I have to apply a longer duration of time to collect data, input data and output data from this system. If I need 4,000 data, it's too much. Okay, it will take me a lot of time before I can predict this system. Okay, so how can I immediately design controller? It's not possible, isn't it? If I want to immediately design the controller, it's not possible. All right, so if I use recursive least squared on the other hand, okay, so if I use recursive least squared, all right, what I can do is I can let the data collected every time, okay, but at one time I can just use 4 data to actually from UK from k equals to 1 until k equals to 4, okay, at any time. At any time, and I can use it to predict this system, because least squared recursive least squared require only that that amount of data to predict. So when I do the prediction, I will get my transfer function beta, okay, or I can get transfer function of beta, okay, and then from that beta I can use it to find out what is my predicted output of the system, and then I can compare the predicted output of the system with the actual output of the system, okay, and I can use that error, okay, to update this transfer function. Then I will get a new set of beta, okay, and then again I can use it to predict more output, okay, and then I can get better error and so on and so forth. So I will do this continuously, All right, I will do this continuously with new set of data at any time. Okay, so what happened is that using this recursive least squared, I will transmit this into my controller development. So this data is called identifier or parameter estimator. This is parameter estimation. Okay, then that data will be used. Let's say I already got my beta, I give that information in this can be done in MATLAB. Okay, in your one loop you can put all these. All right, then you get your transfer function of B over A, isn't it? Your predicted transfer function, isn't it? Okay, then you can quickly use this in your Simulink to design your controller. So you want to design, oh sorry, it is the other way around. Oops. So I can use that recursive least squared to give the transfer function to my system here. So this is my system. Of course, this is not the actual transfer function, it's the predicted transfer function at that time. Okay, and this transfer function will change, okay, with the new set of data. So every time data comes in, okay, your recursive least squared will estimate for you the new data, and then you can use that data as the model of your system when you want to design controller for your system. Okay, so this is on the simulation part. Okay, this is the simulation. This is the real world, the actual, when you get your data from vibration of flexible structure, from your furnace, from your air conditioning system, from your automation, your robotic structure, from your automotive suspension system, and all this. Okay, so this is data from real. Okay, this is from real world, real application. Okay, so what happened is that you use this within the simulation first and foremost to do parameter estimation, and then using that parameter estimation at any time, this parameter will be transferred, okay, to your simulation environment to design your controller. So you want to find out what is this controller, right? So you put it in this form, okay, to design the controller. You give a reference signal here. Okay, of course, this is from the real input. Okay, you can use that also as what you want to control the system. Okay, and then you can predict the output of the in the controller side. Okay, so if this controller is working well, okay, the transfer function of the controller can be used here in the real system. So in the real system, we will transfer that controller, okay, into your real controller. So the real controller will be put here, okay, in your system, similar to the one that we have just now. Okay, so your real controller will be taking the input, compare with the reference, what you want your system to be. Oops, it's really bad drawing I have here. Let me just redraw for you here. Okay, so you can put that predicted controller that you simulated. This one is your simulation controller. You can use that simulated controller in the real application. So this is where your actual controller using the parameter that you have predicted in the simulation environment. Okay. And this process, guys, can be done automatically at any time. So means to say, this parameter of your controller is changing using this one is taken from your simulation. Okay, so the controller from your simulation is taken, read, and then transmitted to your actual real application. Okay, so then your real application will then that controller will be, of course, when I put just one pen here, maybe I have actuator and whatnot, isn't it? There will be actuator there in between, isn't it? Okay, so I should have one actuator here that actually move the system. All right, for example, you've seen when I derive the suspension system, we have actuator here is the force actuator, for example, to actually push your system up and down so that the reference signal is maintained at the required setting point, isn't it? Okay, so but then the value of that controller is coming from your simulation environment. So how do we decide if it's correct or not? Of course, by looking at your output. Okay, so if the output is very close to your input and your error is very, very minimum, then it means to say you have designed a very good controller. So therefore, that value of controller can be submitted to your actual implementation of the actual system. All right. So this is how it works. So for example, I give you an example. For those who, I think some of you have been in Malaysia, you know that I don't know if you know, Malakoff, for example, is a company who developed who actually produce electricity for Malaysia. Okay, and it is placed the plant the apa ni, the plant who produce this electricity plant is in Tanjung Bin. It is in Johor. Okay, so they actually produce electricity to put in the national grid. Okay, so what they do is actually they have a one simulator rig. Okay, to, because all the parameters of the system is being used having controller. Of course, we cannot control with one controller here to control the whole plant. Okay, but the plant is transmitted or is transformed into sub plant. So we have small plant, okay, and it is integrated to become a huge plant for your electricity producer. Okay, so this plant, one of them, okay, let's say take one of them and they develop a simulator, okay, to actually simulate how does the control looks like. So they don't really only use, of course, in this kind of application is very crucial, isn't it? So they don't just really use simulation. So they will put the controller that they have simulated in the simulator first, okay, and check if the simulator is performing like what they want. So if the simulator have performed the way they want it, then that value of the controller will be transmitted to the real system. So there are two ways. Not necessarily from the simulation environment, you will submit the information directly to your actual system. Okay, so you might want to have a tester first. You want to test it on a simulator first. Okay, of course, it's an experimental rig. Okay, maybe the plant is actually put in the lab scale simulator. Okay, so then if it's working perfect, then only they will transmit it to the real system. Why? Because the real application, the real plant costs millions, isn't it? So we don't want to design a not so good controller and transmit it to the real system immediately. Okay, nobody will allow you to do that. Okay, so maybe we submit it to the simulator first. Then if the simulator is actually doing very well, then we can actually use it on the real system. Okay, so this is why as I say, this is why recursive least squared is better compared to least squared, because every second you collect the data. After, let's say you collect the data every 1 second, so every 1 second you collect the data. So after 4 seconds you already have 4 set of input and 4 set of output, isn't it? Okay, so the moment you have enough data, recursive least squared will estimate for you your parameter. Okay, so then once you have estimated your parameter, you can check the performance. You can actually try to check if it's giving you low error or not. Okay, but anyway, even after you check, new 4 set of data already comes in, isn't it? And the moment the new set comes in, again the parameter will be updated. Okay, so every 4 seconds the parameter of your system will be updated. Okay, now that you have if you use 4 seconds, it doesn't need 4 seconds. You can just do it every 1 second. So you use the previous 3 with the new 1 second, the new data. So you use the previous 3 with the new data. So the data that you use, truncation of data, is actually moving forward. So every new data comes in, you can update your parameter beta here, and then you can immediately transfer that parameter into your simulation, and then check with that new simulation, just use it there, and then design your controller. Okay, so I will show you later on in adaptive control how does that works, okay, in actually improving your controller. For adaptive system, guys, so this is actually can be also used for actual for normal control, but for adaptive system, this controller, okay, will be using the improved parameter. So that parameter will also use to update the transfer function of your controller. So the parameter of your system will be utilized to update the transfer function of your controller. Okay, and then once the transfer function of the controller have been tested correctly, so then it will transmit it to the real system. So this can be done automatically, okay, and it can be done continuously. So this kind of problem, if you use this kind of controller, it called hardware in loop. So for hardware in loop means to say you can have your hardware. This is your hardware, isn't it? From the real, oops, why do I do that? The hardware is actually coming from the real application. Okay, so data from the real application first and foremost will be used for your identification, and then once it's been estimated, you can use it for your simulation to do what? To design your controller. Okay, so that is why recursive least squared is better compared to least squared. Just imagine if I want to use least squared, okay, I need to collect 4,000 data first. Okay, so there will be a long delay before I can actually estimate the parameter using least squared, right? And then every time I want to update the parameter, I need to wait for the new set of 4,000 parameter. If one parameter per second, then I need to wait 4,000 seconds before I can update the system. All right, so this is not very it's not going to be real time. Okay, the implementation cannot be real time updation of your controller. Does it make sense or not? Is it okay? Are you here, guys?
Yeah.
Yes, Professor.
Okay, so
Yes, we do. Thank you.
that's good. Okay, that is why when I use least squared parameter here, I mentioned that this is the old data, this is the old phi, this is the old zeta. Okay, then when you want to use least squared, you need to have one new data. From that one new data, you will get one new phi. Okay, of course, there will also be one new error, isn't it? But we're going to ignore that error, isn't it? We're just going to focus our y, our phi, and our beta. Okay, so that new scale is here. So this new data, okay, if you think of that data as a huge data, so for example, for ARCS model, let's say second order, let's have model order y is equals to ARCS model with second order. So your yk, if you remember, yk is equals to, let's say I'm using bz minus 1 plus b1 z minus 1 plus b2, model order 2, okay, over 1 plus a1 z minus 1 plus a2 z minus 2. Okay, so what happened is that if I cross multiply, I'm going to have yk plus y1 a1 yk minus 1, isn't it, plus a2 k minus 2. Okay, and the other side also I will have multiply with u, sorry I forgot that. So multiply with u, you're going to have b1 uk minus 1 plus b2 uk minus 2. Okay, so sorry about the handwriting. Okay, but you understand what I'm trying to say, right? Okay, then you have that, then you're going to rewrite this, and you're going to have y k is equals to minus a1 y k minus 1 minus a2 y k minus 2 plus b1 u k minus 1 plus b2 u k minus 2. Okay, so then you have this, you put it in a matrix but only with one row, because we're going to read the data one data at a time, not like least square. Least square I have to collect a batch of 4,000 data, so my fee have to be 1,000 fees, isn't it? 4,000 for example. But for recursive least square, only one row of data with your parameter you want to estimate, isn't it? Okay, so this is the value that I mentioned. Okay, xt, it is actually representing this value of one row when k is equals to 1, for example. Of course, I need to do the shifting and everything, right? Remember from the last time, we need to shift this, okay? So, of course, you need to shift this, okay? So, we're still going to follow that regulation where we're going to shift it so that it will start with ym here, okay, for new data, right? So, this is going to be just one row. So, when we have one row, when you apply your least squared estimation again for recursive least squared, so you're going to have, this is the previous data. I'm going to put different color for that. Okay, this is your previous data, previous data, previous data. Okay, using your least squared estimation here, right? Okay, then this is the new one row of new data. This is one row of your new data. Okay, and then from there I do cross multiplying of my matrix. This is where it become a bit complicated. This is where it become very tedious and very complicated. Okay, so this is what I meant. It take me ages, so I don't expect you to understand it within one week or one slide or one presentation from your lecture, isn't it? Okay, so I just multiply that with that, it become here, isn't it? Okay, then multiply that with that, it become here. Okay, then I multiply this with that, it's become here, and then multiply this with that, and it become here. All right, then we expand this, because you know phi transpose n have 1,000 data, phi transpose and phi n have another 1,000 data, and then this is just one data, this is just one data. All right, so that is why we need to have some simplification. So this is when it become very tedious when I do the simplification. Why I do the simplification? Because I need to write it in this form. Okay, so I need to write it in this form. So I introduce two parameters. The first parameter is the gain k. Can you see that? The gain k. All right, and another parameter is your beta m. This is your actual, so this is just beta gain k, actually just gain k, but that gain k is here, okay, and that gain k is having new things, which is pn and lambda. All right, then lambda and pn is defined as this equation that I have here. All right, so it is actually coming from your matrix being expanded. So I cannot show you here because I don't want to put it in a matrix form. Okay, but when you expand your matrix, you can write this simplification. Okay, so then it is simplified, saying that the new parameter is equals to, sorry, let me just erase this again. So it just show that the new parameter is equals to the old parameter. This is your new parameter. It is equals to the old parameter plus gain, the gain that you need to calculate, okay, using this formula here. That gain, of course, we want to calculate the gain, you need to know your P and your lambda. This is how your P and your lambda behave. Okay, how do I get that? It's coming from the expansion of the matrix that I have. All right, so this is why it become very complicated, and don't worry, not going to be asked you in the exam and all. Okay, yes, the derivation is very complicated actually. Okay, and then that multiply with what? Multiply with your new. Can you see this is the y is actually your new data, your yn plus 1, the new data. okay, minus the new data xn, okay, yn is the new output, xn is the new fee, okay, fee is the collection of output and input, right? Okay, the new fee multiplied by your previous data, your previous parameter estimation. So you have your old estimation, this is also your old estimation. This is your new fee, okay, this is your new y, new output, okay. So when you have your new fee multiply with your old prediction, you will get your prediction error, okay, you will get your predicted output. So this is all a new fee multiply with old estimation, that part, this part here will give you your predicted output, okay, predicted output when? Predicted output at n plus 1. Okay, so that is your predicted output at n plus 1. So when I have my predicted output, I will then, when I minus with my new output, okay, I will get what we call prediction error. Okay, and that prediction error is being multiplied with gain. Okay, that gain is coming from my huge metric expansion just now. Okay, so that gain, if I have my lambda is lambda is actually forgetting factor between 0 and 1. Okay, so if you look at the value of 0 and 1, it will actually also play important roles on my gain. Okay, so please have a read about forgetting factor and then find out how does it work when we have it between 0 and 1. It cannot be 0, it cannot be 1, it is either 0.1 onwards until 0.98. Okay, 99 also you can do, but it's 98 is actually suggested by the researchers. Okay, so when we have this old estimation added with this new prediction error multiply with your gain, you get your new estimation. Okay, what happened if your new estimation have no improvement? So it means to say your system doesn't change at all over the next, when you collect the data, you keep collecting data, isn't it? But your system parameter doesn't change. So when it doesn't change, your prediction error will become 0. When your prediction error is 0, you multiply with whatever gain, it will still be 0, isn't it? So that part will remain 0. Okay, so when your system doesn't have any changes, okay, when it doesn't have any changes, that prediction error multiplied by gain will become 0. So your old estimation, your new estimation at that time will be the same as your old estimation. You get it? Okay, so it means to say you can do your recursive least squared at all the time. Okay, so but only the parameter will only be updated if there is any changes in your parameter. If your parameter doesn't have any changes, your estimation will remain the same. Why? Because the prediction error will actually tackle that part, isn't it? The prediction error, if the prediction is 0, okay, the prediction error is 0, means to say the actual prediction and the new prediction and the old prediction is the same. Okay, so the prediction error is 0, so your parameter will remain the same. Your parameter will be updated when once you have a prediction error started to become you start to have prediction error. So this is when I put in my algorithm. This is very difficult to understand, but that's how it is. Okay, that P, the new parameter I have given just now, it is in this form where you have diagonally multiply with a large number. Okay, it is alpha multiplied by I. I is an I matrix in MATLAB. Okay, lambda is actually a huge number. Okay, and that P value will be updated as well. Okay, as you do your prediction, the P value will be updated as well. Okay, that's why I put here P n plus 1. So every new data comes in, your P will be updated too. Okay, and your Kn also plus 1 means every new parameter comes in, your K, value of K will follow these mathematics. Okay, all right? And then with that mathematics, you get a new value of your gain, all right? And then with the new value of your gain, will you use this mathematics, you get your new value of as parameter estimation, provided that your prediction error is not zero, then your parameter will be different than the previous estimation. So if you do 1000 data estimation, you will have 1000 parameter estimation, okay? But however, the value between the parameter estimation can be the same, okay? Maybe there's some point where the value is the same, okay? So when the value is the same, it simply means that during that time, the parameter or the system doesn't have any changes in your parameter, okay? That's all. So then I put this in MATLAB. But in MATLAB, you see that the recursive least squared, I give a whole bunch of data. This is because I don't have the hardware in loop, isn't it? To show you what happens when the data is collected one by one. But in the MATLAB programming, I put it, even though it is not, it is a bulk data, but I put it in the loop where the data is read one by one. As if in the real system, the data is submitted one at a time like this, okay? When the data is given one at a time, okay? So this is how you use recursive least squared. All right, is there any question on recursive least squared? Which part you don't understand? It's not very clear.
Well, can I?
Is it clear?
Just a question.
Yes, for us.
Why use the lambda and the last question?
Okay, the reason why I use lambda is because from the derivation there's some forgetting factor, because we want the beta, how much you want the previous value to remember or to forget. So if your value of lambda is high, your forgetting factor is very high, means your new parameter estimation will be completely different than the previous parameter estimation. But maybe when you have your system, parameter estimation should not be too much different. It might be within certain range, isn't it? We do not know that range, okay? So that's why we have that lambda, to make sure that the parameter of your system doesn't change so much. Maybe change so much means maybe in the beginning your parameter A is 0.1, okay? And then the next cycle, you don't want it to be completely different. Maybe it becomes 100, okay? It's completely different, isn't it? So that's why you have that lambda, to ensure that the variation of parameter is within certain range. But that range is unknown. So that's why you use lambda as just a forgetting factor. How much your information being forgotten. Okay, so when your if lambda is 0, means to say your forgetting ratio, forgetting factor is 0. It means to say it doesn't forget at all. The value of beta is the same as the previous value. It doesn't forget at all. It remember the value of the beta. Okay, so it doesn't change at all. If it's 0.1, it keeps 0.1. So this one is not required, is not wanted as well, because if the parameter of your system change, then your system will not detect it because your lambda is 0. Okay, so you need to range your lambda, but the value of lambda is unknown. So it is something that you need to play around with when your simulation, during your simulation, you have to do a trial and error to find which one is the most desirable, okay, the value. Which one is okay? You do not really know what is the actual, the value. When you do simulation for, especially for this kind of problem, it is a parameter estimation problem. So it is estimation. So estimation means there's a lot of assumptions, isn't it? You don't know real what is the value. If you want to know the real one, you do mathematical derivation. Okay, but in estimation, you have to have a sort of certain range where you do not know. So you put that as a unknown, so you put that, you get that value by just trial and error, and as long as it is within the estimated error that you can tolerate, then it should be okay. All right. So for example, when you estimate your parameter using for a flexible beam, for example, then you get the parameter estimation is 0. Let's say your parameter estimation, you predict your error, you get your error is 0.000001. This is very good, isn't it? Okay.
Yes.
And then compare to another one, you have 0.0001, which is better. Of course, the first one is really accurate, isn't it? Very good, very, very accurate, because the error is very small, isn't it? Okay. However, when you use your sensor to detect the error, can it really detect this small error? Your sensor, can your sensor have that precision? Okay, sometimes sensor can only go to up to 4 significant figures, isn't it? Okay, so even though your sensor, your error is very small in simulation, but you have to look at what are the sensors that you have. Is it really needed or not, this kind of precision? Okay, so sometimes even with that kind of precision, you cannot see, your sensor cannot detect it already. Okay, so you don't need to have that kind of precision. Okay, so maybe your sensor can only detect 0.01. Okay, so in that case, both of these should be okay. All right, so when both of these should be okay, if my sensor can only do that, I will go for this one. Why? Because if I want to do this one, of course I need to have more data, I need to have to be very specific, my error must be very small, so I have to have a lot of I have to predict it more, very, very accurate, so I have to do a lot of loops and all. So maybe it will take longer time, maybe it will take more data. Okay, so I can settle down with this kind of prediction. Why? Because my sensor will only detect that. Okay, even maybe on vibration, when you have these two situation, your eyes cannot even see it vibrate anymore. The sensor can only see this kind of values when it vibrate. Okay, so even you have your system very accurate, error prediction is very, very small, it doesn't make any sense on the physical system. Why? Because both of them, your sensor will detect it as 0. Okay, all right.
Okay, doctor.
Is there any questions on this? Okay, so if you don't have any question, I want you to go through the MATLAB. I don't have my MATLAB here. Or do I have it, MATLAB here? I want you to go through MATLAB and have a look at this. I think I've shown you. Let me try to open my MATLAB here. Okay, I think I've shown you, isn't it? But, oh, hang on. That's why for recursive least square, I just want you to understand how it is actually done using your MATLAB programming. Okay, so I'm not going to ask you to derive it or anything on your examination or whatnot. Okay, and of course, to understand the derivation, it will take you time, because it does take me time as well. But you are cleverer than me, so you take shorter time to understand it. Okay, let me just try to share with you MATLAB programming. Once it opens, it takes longer time to open. Okay, so what I want you to do, not recursive least squared, because I already gave you recursive least squared, not least squared, because I already gave you least squared programming. I want you to try to understand those both algorithms, and then I want you to try to use the least squared and the data that I gave you to develop generalized least square. Means to say you want to update the least square so that you can actually improve your reading. Okay, let me share you MATLAB. Okay, can you see MATLAB?
Yes.
Okay.
Yes, Prof.
Have you ever used MATLAB before? Okay, so if you haven't have the MATLAB, you can download it at UTM software. page software link through if you're outside UTM, you can use VPN, and then you can access the resources, and inside that there is a licensed software for MATLAB. If you want to buy MATLAB, it's very expensive. For education, I think the whole set costs about 30,000 or something. So it's very expensive. Okay, so use the one that UTM have bought, the license that UTM have bought. Okay, I think UTM have unlimited license user, so you can use it. Okay, and okay, I've already shown you least squared. Okay, so this is least squared estimation, where in the beginning, you can see I load the data and then I plot the figures for you just to see, and then I give you the parameter estimation. The NP is actually the number of parameter that you need to estimate, and then MO is the model order. So MO, what is ever the model order, okay, the number of parameter is divided by 2. So that's your model order. So you need to decide what kind of model order. Of course, for parameter estimation, you do not know the model order, isn't it? You have to you have to try and error. So normally what I do is I try with the smallest number first, and then it will actually if it's not giving me the error that I want, if it's not giving me the good estimation like I want, then I will increase the number of order that I put here. Okay, so in this case you can see I use 4,000 data, even though the data that I have for this algorithm for this data that I've collected is more, 6,000 data. I use only 4,000. Okay, so this is the loop where you want to build your fee. You remember fee is actually a very lengthy matrix. You need to put all the data inside fee, the output negative y and also the input x. So this is how you put in your matrix here. Okay, so you can try and error and run this and check what do I mean. I might make some mistakes there because I write this in a hurry. So if I have any error, please correct me. Okay. And then this is as simple as that. Your beta estimation is just the inverse of phi transpose multiplied by phi transpose multiplied by y. The y, I call it y here just to differentiate between the data collected and the data that I'm going to use in my modeling here. Okay, then as soon as I predicted beta, I just multiply with the phi that I have developed here. The phi that I have developed here, I use it again, multiply with beta, the predicted output, I will get it, I call it YP. Then I got my error, and then I calculate my mean square error, and then I plot my algorithm. So if you run this, can you see hang on, can you see the figures? You cannot see the figures, I think.
Not yet.
Can you see the figures now?
Yes.
Yes, Prof.
Okay, so this figure, the first one, the blue color is your input, the red color is the output. Output is the vibration, the input is maybe the torque given to the system, because you want to disturb the system so that it moves, isn't it? So we give a torque, it is actually changing using PRBS. This is called PRBS input, okay? Pseudo binary random input or something, PRBS. Pseudo binary. Can you Google for me PRBS later on? PRBS is pseudo with a P. The spelling is PSEUDO or something. Okay, binary random system. Okay, so this is the input, and then I give the output here. This is the output that I get. So if you imagine that this is collected from the real system, okay, this is the data that we will use for our estimation. So then when we done the estimation, this is what I got. Can you see? All right, this estimation is very good actually. You can see it, the data is overlap between one another. So the red color is the predicted one, the blue color is the actual data that given to the system. So then we later on can plot the error. So the error is very small actually. If compared to the sensor that we use to detect the error, maybe in reality we can see that it is the error is 0. Okay, but when we actually collect on simulation, of course we can see there's an error there. Okay, so using this predicted output, what I do is that, guys, if you look here, let me just, sorry, I'll see. Okay, so I have, if I type beta, okay, so this is the value of my A1 so I use model order 2 just now, remember? So the first value is my A1, the second value is my A2, the third value is my B1, the fourth value is my B2. Okay, so that is a beta. So for least square, just gonna get one set of beta with that 4,000 data. So just imagine if you collect that 4,000 data, you one data at 1 second. So you need 4,000 seconds before you can get your data estimated. So that will take time, isn't it? So if it's a suspension system, while your car is moving through a rough terrain, rough road profile, so what happened? You cannot design the controller. You need to 4,000 seconds before you can actually update your controller. Remember the parameter used here to update your controller, isn't it? To design your controller, isn't it? So you need to wait 4,000 seconds before you can actually calculate your error. Of course, the prediction will take shorter time, only a split second just now. But data collected need to collect more data for the prediction. Okay, so you understand what I mean there? Okay, so if I use
Yep.
recursive least squared, so I'll show you recursive least squared. Of course, in this case, I also collect the data at one time, a bulk of data. But in reality, I can just read the data. So I don't have to collect the 4,000 data. I don't have to do it, okay, for recursive least squared. Why? Because I can read the data, one data at a time. You can see in this loop, this is the difference. Least squared, you can see the parameter estimation is outside the loop. Okay, so it means to say I have to have the bulk of data first before I can do my prediction. However, for recursive least squared, you can see the beta is estimation is done in the loop. So it means to say, if I collect data, if you imagine this loop as collecting data, one data at a time, okay, and continuously, you can use the data later on, right? So you're going to continuously create the new row of your fee, one row at a time. I'm not going to use all 4,000 data. I'm just going to use one row. It means to say that one row contain how many? It depends on my model order. If my model order is 2, then that row will have 2 output and 2 previous input only. 2 previous output and 2 previous input. That is considered my new data. And then I can put in this mathematics and then I can calculate my parameter straight away using that 4 data. 2 previous input and 2 previous output. And then every second, if I keep collecting that data, okay, I will predict it every second new with the new set of input and output. Can you imagine that? So just imagine this loop as if I'm collecting data every now and then. Even though I put the data, all the data here, okay, because this is simulation, of course I cannot show you what happens if I have data one at a time. You can just imagine that loop as the one that actually giving the data to the prediction, only one a small set of data at one time. Okay, so every loop you will have new set of data, okay, updated, and then from there you can see I will predict the parameter at every loop. Okay, so when the parameter is predicted, you can see that the previous parameter beta, so for the new parameter, the previous parameter plus the gain k, okay, multiply by the error that I have calculated. You can see, okay, in this loop, first of foremost, I explain my new data. Okay, it is actually a collection of previous 2 input and 2 output. And then I multiply what I call it here inverse lambda, that L here is lambda, multiplied by P. I already put the value of P in the beginning. What is the value of P? And then multiply by my new data. Okay, that I just call it XX to simplify my equation. K is inverse of this value, multiply with XX, and then P is equals to this inverse of lambda, multiplied by P minus this value here, and then I will get my prediction output, okay, based on the previous, based on this new set of data, multiplied by the previous estimation. And then I will get my error, that's my error, and then the new estimation is equals to the previous estimation. You see here, the new estimation is at the value of I. Okay, so whatever the value at that time minus the old estimation, you can see here the value is I minus 1. So the previous estimation is being used plus K multiplied by the error that I have estimated. The error that I have estimated is here, Y, actual Y minus predicted Y at time I. Okay, so that the new estimation is done every now and then. Just imagine this loop is by me collecting the data from the system at every time, every 1 second, for example. Okay, so that every 1 second, my parameter will be estimated. Of course, if the error here is 0, mean I don't have any difference between the actual prediction and the previous prediction. The actual predicted actual value and the predicted value means there's no changes. So when there is no changes, my parameter Bn will remain as the previous parameter. It doesn't have any change because this is 0. 0 multiplied by k becomes 0 plus the previous value. So the new value will become similar to the previous value. Okay, if I run this, okay, so my mean square error is given there, and this is hang on, let me just show you my prediction. So this is the input and output again, the same data used. This is my prediction. It's a slight, sorry, this is my prediction. You can see the data is not really overlapping, so there are some slight error between actual and predicted, but it's not too bad. You see, it's not too bad actually. Okay, so you don't need to sometimes to make it very precise because even your sensor will not able to detect this kind of error. Okay, so it's not too bad. It's actually following the pattern, and it's actually not really different than the predicted one. So once you have predicted this, okay, let me just show you the value of beta. So the beta is a lot. You see, if I have 1,000, can you see that? When I have 1,000, when I use 4,000 data for my estimation just now, I will have 4,000 beta. Because why? Because at every loop, okay, the new beta will comes in, okay, and the changes of beta may be not much, okay, and then some point maybe the beta doesn't change at all, okay, but the new set of beta will be estimated at every time, okay. So it means to say I only need, for my recursive least square, I only need to have a set of previous 2 input and 2 output from the previous data to update my new one. Of course, in the beginning, my prediction is not very accurate. Let me just show you here. In the very beginning, maybe the prediction is not very accurate. In this case, it's still accurate. But sometimes you see in the beginning, the error is even more. Okay. But towards the end, the error is become much, much less. Okay. In this case, the error is less in the beginning. Okay, but actually, some system, the error is more in the beginning when you start to want to predict the value of beta. But the moment you got your value about the correct value, then the beta is only updated based on changes on your system. Okay, not because of the prediction error anymore. All right. Okay, any question on that matter? No. Yes. Saleh, you want to ask questions?
No, it's clear.
Is it okay? Right. Is that clearing your apa ni, all the question that you asked me?
Yes,
Yes. Now better, clear better.
Okay, great. So it means to say after this, you don't have to worry with the derivation of recursive least square. I just want you to understand how it's being utilized for your system prediction, from your system identification, okay, to predict your parameter. All right, because I'm not going to ask you to, I'm not going to give you a set of 10 data and ask you to predict using recursive least square. It's difficult.
Yeah.
Okay, so I'm not going to do that. All right. Okay, now, okay, I'm not going to, if there's any question, there's no question, I'm just going to start my adaptive control on the next class. So I will record the session on Thursday. I will send you the session on Thursday for you to view on adaptive control, okay? If I can have online discussion like this, then I will do online, but Otherwise, I'll send you the recorded session for adaptive control. So for the next session, we will start on talking about adaptive control. So for the system identification, it is up to this point where I introduced to you least square, generalized least square, and recursive least square, and also how to use it within MATLAB. Okay. So the next class, I'm going to show you on adaptive control and how does this recursive least square will help us on designing our controller for adaptive system. Okay?
Okay.
All right. So for the time being, later today, I will send you a Word document asking you to conduct your second assignment on parameter estimation using MATLAB programming for generalized least square. All right. The data is already given to you, right? So you can use that data. Okay. With that, thank you very much. If you have no question, then I will end the session now. Okay?
Thank you so much, Doctor.
Have a safe staying home.
Thank you.
Take care.
Yeah.
Study.
Already, yes. Yes.
Okay.
Bye-bye. Assalamualaikum warahmatullahi.
Waalaikum.
Waalaikum assalam wa rahmatullah.
Ayat, you can go to sleep now.
Ayat and Omar.
Ayat and Omar, they kept joining the class. I'm so sorry for that. Okay, thank you guys. Assalamualaikum. Bye-bye.
Thank you.